Hi there. Now we're going to go over the hash table data structure, right? And in my opinion, the hash table is the most powerful data structure there is in computer science. And the reason for that is if you want to get something from this data structure, if you want to retrieve a value from the hash table, the running time of that operation is big O of 1, okay? As you're aware, this is instantaneous, right? This is constant running time. This is much faster than the binary search, right? So this should blow your mind. If you want to insert values into the hash table, that's also big O of 1. Constant running time for insertion as well as retrieval, and in many cases for deletion as well. It's constant running time. So this blows away all of the other algorithms and data structures that you've been learning in this course, this hash table data structure, okay? And believe it or not, a lot of computer algorithms are based on this hash table, a lot of computer programs. For example, the spell checker. When you're typing in a Word document, the program needs to be super fast in determining whether what you're writing is spelled correctly, right? It can't take a second or 2 seconds. It needs to be instantaneous as you're typing along, real time. So the hash table data structure is used a lot in many programs where you need that type of speed, okay? How does this work? Well, believe it or not, the hash table is actually a very simple data structure. It's simpler than some of the trees that you've seen, the heap, the binary heap, the binary search tree. It's simpler than that, all right? And there's beauty in simplicity. I don't know if you've heard that saying before, but I don't mean to be cliche, but in my opinion, this is a beautiful algorithm because it's, first of all, simple, and it gives this awesome performance. So how does this work? Well, in the background, the hash table, let me just write that up here again. The hash table is using an underlying data container that we're all very familiar with by now, and that is the array, okay? Now, other data structures also use the array, but the way the hash table uses it is closest to the nature of how an array should be used. When you're inserting data into an array, all you need is the index position, right? And if you're getting a value from the array, all you need is the index position, right? And because we have this index position for insertion and for retrieval as well as deletion, the running time of these operations, because it's an array, is big O of 1. So the hash table utilizes this concept of index positions, and that is why we achieve this big O of 1 constant running time operation. So how does it do this? You know, let's say that we have 100,000 words in an array, and we need to get the correct spelling of a word. Let's say the word is something simple as hello. This hello is stored somewhere in this array, and I'm just going to add an ellipsis here to indicate that this is a much bigger array than I've drawn. So hello is somewhere within this large array, okay? How is the hash table going to be able to retrieve this hello word, right? We need to get the index position, right? How do we get the index position? Because this hello could be somewhere in, the 1,000th index position. Let me write hello here. We need to know which index position this word resides, or this object. It doesn't have to be strings, it could be objects. How do we get the index position of this? Well, the magic happens with the hashing function. All right, this is the key term right here, hash. If we pass in the word hello into this function, let me just write that down here, hash func. And I'm going to be defining this function in the Java code, and you'll get a better understanding of how to code this. But basically, if I pass in the word hello to this function, the magic is happening in this function. It's going to tell us the output of this function, its return value, is going to be the index position. So let's say the index position is 182, for instance. This process of getting this index position is instantaneous, right? Because the hash function has a way of mapping words to index positions. The logic that's coded in the hash function is basically going to map objects to index positions. And we'll go over the different ways in which we can do this. But Java has this process perfected. We'll certainly go into that later. But we got what we needed. We pass in the string hello to the hash function, we find out that it is in slot position 182. So now we know that hello is in 182. So if we need to get it, all we have to do is reference the array at the index position 182, and we have the word hello, right? And this word can have, it could be an object, it could be all kinds of things. It could even be another array or linked list that we get at that index position. But the key is to get the index position, which we've got because we use the hash function. So what is the concept of hashing? Hashing converts objects to index positions in the array. It's sort of like an address locator. That's another way of looking at it. The hash function is an address locator. It gives us where the item that we're searching for is located in the array. And once we have the index position, you're well aware that things are immediate, right? It's very fast. Big O of 1. We just need the index position. And that's what the hash algorithm allows us to do. So what's going on in this hash? Let me clear the screen here. We need to think about how data is stored in a hash table. Let's say that we're trying to build a dictionary and we have words like, for example, apple. I'm just going to write a few words here. Cat, hero, dinner, elephant. And we need a way to insert this data into the hash table so that we can also retrieve it very easily. Well, we need to use the hashing function. So I'm just going to write that here, hash func. And the magic is within the logic of how this function or this method is coded. All right, so we pass in apple to this function, and it's able to basically give us the index position of where apple belongs in the array. So let me just draw an array here. So let's say that this function takes the first character of the word and maps it numerically. Which alphabet number does A represent? In this super basic example, let's just go in numerical order and say that A is going to represent the number 1. All right, so let me just write that up here. B is going to represent 2. C is going to represent 3, all the way to the 26th alphabet, which is Z. And let's just say that the hash function has this mapping put in place, and it just figures out what the first letter is of this word and gives us the index position. So in this case, hash function is going to return us the index position 1. So we can very quickly go to the index position 1 and get, and that's going to be right here, index position 1, because we know that this is 0. And let's just say that this returns us the word, right? We were able to retrieve the word and as well as insert it. We insert the data using the hash function, and we retrieve the data also using the hash function, because the hash function gives us the index position that is involved for that given word. All right. So for example, cat, the first letter of cat is C. So the index position 3 applies here. So the hash function is going to give us the number 3. So we put cat in index position 3, which is right here. So going to the next word, hero, that starts with an H. So where will that be? Well, let's just draw a few more slots here. So 3, 4, 5, 6, 7. H is going to be right here. Sorry, this array is getting a little messy, but let's just say that we put the word hero in this index position. So the hash function gave us where to put it, and when we need to retrieve that value, we pass in the word to the hash function and it gives us that. I'm going to repeat this multiple times because this is a key concept in the hash table. Dinner goes into the 4th index position, and elephant goes into the 5th index position. Now what about if we had another word called Africa? Now we're in trouble because apple starts with an A and so does Africa. So the hash function, what is it going to return for Africa? It's going to return 1 for Africa as well. And we can't put Africa into this slot. So this hashing function is no good. As a matter of fact, this is a terrible hashing function, but for the sake of keeping things simple, I showed you what a hashing function is. So let's look at a way to improve the hashing function we're using and make it generate more keys for us. Let me clear the screen to make some room. So these are the words that we're trying to insert, and the hashing function was giving us a problem, right? It was not a good hashing function. The maximum number of index positions that function could generate for us was 26, because if we are only considering one letter of each word, right? The first character of each word, that's going to give us a maximum possibility of 26. And that's only the case that all of the words have a different first letter, right? So if we try to enhance along the same lines, and let's say that we want to involve the last character of each word as well into the computation. So what we could do is A for apple is in the position 1, and E is in the position of 5. So what we could do is we can add 5 plus 1, and that's going to give us 6. So we can put apple in the index position 6 in the array. And so Africa, there won't be a conflict. First character of Africa is A. The last character is A as well. So that's 1 plus 1 is equal to 2. So there won't be a conflict between apple and Africa. However, this is still not a good hashing function because, for example, the word announce has an E at the end. And so that is going to be the same situation as apple. We're going to have a conflict. Both announce and apple are going to try to go into index position 6. So both of our hashing strategies were no good. We can't just involve the first letter because that's just only going to allow 26 possibilities of words if the first letter of the word is unique. And if we involve the last letter, that's another 26. And if we involve, some of the middle ones, let's say that we're talking about a 10 character word, that's 26 plus 26 all the way to 10 times. That's going to give us a total number of 260 words that we could put in our hash table. And this is obviously only if we get unique index positions for each one of those words. So there's got to be a better way to hash strings and other objects. And I'm going to show you in the Java code how to create a very good hashing function for strings. And that's going to actually involve the modulus operator. So just a quick review from several lectures ago, the modulus operator is used to find the remainder. So if we do 9 modulus 3, that's going to give us 0. If we do 7 modulus 3, that's going to give us 1. So using this along with a good hashing strategy is actually going to improve the variety of index positions the hash function can generate for us. So we'll go into those details later, but understand one very important thing that I'm about to talk about. And that is that even if you have a very, very good hashing function, you will still experience collision, okay? There will still be conflicts. So let's talk about how to resolve these kinds of conflicts, conflict resolution. So let me just draw an array here, and I'm going to hopefully try to keep this much neater than the previous whiteboard that I had. So let's say we try to insert the word phone. So we give this word phone to our hashing function, and let's say that that's a perfectly working hashing function. It does some random calculations and gives us a pretty good index position to put the word phone in. And so let's say that index position, let's say that our hash function returns the index position x, okay? And let's say that x ends up being somewhere in this array right here. And let's say that there's a word, okay, let's say that there's a word in the index position x where we would like phone to go, all right? So what do? Even with our perfectly working hashing function, we are still experiencing conflicts. So we try to insert the word into this x index position, and we can't do that. So there's a strategy known as probing. We can actually probe to the next cell to see if that's empty. And if it's not, then we probe to the next one. If not, then we probe to the next one until we come across an empty slot. And this is an empty slot. So we'll put phone right here in this cell, okay? So this is actually known as probing. And specifically, this is known as linear probing. We're stepping one step at a time, all right? So if we're not able to insert phone into index position x, then we need to probe to x plus 1, all right? And if that's not available, then we probe to x plus 2. And if that's also not empty, then we probe to x plus 3, and so on until we get to the place where we can fit that word. So the step size that we're taking is 1. We're moving one step at a time to find an available slot. Now this is one way of resolving conflicts. right? And another term for this is open addressing. We're looking for an open address, an open position where we can put the word. And we can use this linear probing technique to do that. Now, even if we were able to resolve the conflict and finally get the word into the next available slot, we still have a problem. And the problem is that we're creating this sort of cluster of words, okay, all jumbled up together, and they're not in their preferred index position. They're sort of just being advanced to the next available slot, and they're clustered together, right? And this kind of a cluster is no good, because when we're searching for phone, what the function is going to do for us is going to give us this index position x, but then we're going to have to iterate to find the next available slot where phone could be. And if we have a big enough cluster, this entire hash table could degenerate to big O of n, okay? And that is no good. That's just searching through an array, and we don't want to do that. We want it to be big O of 1. That's the whole point of using the hash table. So a slightly better way to avoid clustering is to use something called quadratic probing. This is linear probing, where we're taking one step at a time. In quadratic probing, we take multiple steps. So if we're not able to put the word in the position x, we would advance to x plus 1 squared. And if that's occupied, then we go to x plus 2 squared. And if that's occupied, then we advance to x plus 3 squared. As you can see, the hops that we take, the jumps that we take, become increasingly larger. So the quadratic probing is a bit more extreme than linear probing, right? It takes bigger jumps. It's as if the quadratic probe became increasingly desperate as its search length increased, right? At first, it calmly picks the first cell, the adjacent cell. If that's occupied, it thinks that we may be in a small cluster, so it tries something 4 cells away. And if that's occupied, then it becomes a little concerned, and it jumps to 9 cells away, and then 16 cells. And as you can see, it's going to go up like that, 16 and then 25. So this quadratic probing is slightly better than linear probing, because we don't start piling words right next to one another. We do kind of jump ahead and put the word in if we can find an available slot. But that still doesn't save us from clustering issues, right? Because the pattern is still 4, 9, 16. This kind of pattern is still going to be spaced out like that. So we'll have smaller clusters, but there will be clusters nonetheless. So they may be spread out a bit more, but we're still going to have clusters. To reduce the number of clusters even further, we can use a third approach, right? I showed you linear probing, quadratic probing. There's a third approach we can use, and that is known as double hashing. In double hashing, we pass the element that we want to insert to 2 hashing functions, hence the name double hashing. So let's just call them func1 and func2. Let's say we pass the word phone to func1, and that gives us the hash value. And let's just say that that's x. Well, func2, and this x is the index position where we would like to insert phone. And if it's occupied already, we cannot insert it there. So we need another piece of information, and that comes from func2, right? The step size is determined by func2. So we pass the word phone to func2 as well, and that's going to give us the step size. And let's just say that step size is 3, for example. This step size is going to be different for every word. We're going to get an index position, which, there can be a conflict, but then when we involve this step size, it's going to, we won't have as many clusters, right? You may still have a few clusters here and there, but involving a second hashing function is going to reduce the probability of collisions even further. And the step size that's generated by func2, it's going to vary based on the argument that is given to it, right? So it has a different mechanism. It's a different function than func1. It has a different mechanism of dealing with the word phone, right? So func1 has a different way of handling how to generate an index position for phone, and func2 has a different strategy for generating the step size for the word phone, right? And the step sizes will vary based on the argument that you pass to the step size function. So this double hashing actually is the best approach to finding an open address for where you want to put your element into a hash table. Now, a very key thing that I forgot to mention is, and this is a prerequisite, and that is that your array size, right, the underlying array that you're using, its size better be a prime number. And I'll explain to you shortly why that's the case, and it's going to make complete sense when we get into the Java code. We're going to be implementing the double hashing approach in Java. So before moving on to the code, I just want to summarize everything and get you thinking about how you're going to do this programmatically. So let's clear up the screen here. In double hashing, when we want to insert an element into a hash table, we need to pass that element to two functions, okay, to find the ultimate index position where we would like to put it. So the first function, let's call it func1. Its responsibility is to give us the index position of where we would like to put the element. And let's just say that that's x. The second function, its responsibility is to give us the step size. So the number of steps that we would need to jump in order to find an empty slot in the array, okay? In the event that x index position is occupied, okay? So let's say that we're trying to insert the word bottle, okay? We pass bottle to func1 and we pass bottle to func2. Func1 gives us the index position x, and func2 calculates some step size, okay? And we'll go into the details of the calculation later in the Java code. So we get the index position of func1, and let's say that that index position is right here. In this case, we cannot insert bottle into this spot. So what we do is we increment the step size with x. So we do x plus 5, let's say, all right? We'll only know what the step size is once we run the func2, all right? And let's say that gave us the number 5. And that gives us a new incremented x, okay? That gives us a new index position. And let's just say that that's 7. We're not going to move 7 spaces yet. What we're going to do is actually compute another calculation, which is 7 modulus array size, okay? The size of the array. And this is going to give us the slot position where we need to look next for vacancy, for a vacant slot. And let's call that slot xn. So let's say array size is 29, for example. 7 modulus 29 is going to give us a 7, okay? Because 29 does not go into 7, so the only remainder we have is 7. So we try to put the word bottle into index position 7. So let's say that index position 7 is right here. This is the new x, okay? This is xn. So in this case, it's empty, so we can put the word bottle in here. But let's say that there was a word in here as well. What do? Well, we go through this process again, okay? And the process I'm talking about here is this. Put a box around it. We do the calculation again. So xn is now going to be 7, and the step size that we've already calculated is 5. So we do 7 plus 5 is equal to 12, and then we do 12 modulus array size, all right, whatever that array size is going to give us xn, a new x. So let's just call it xn2. So 12 mod array size is going to give us the new xn. And let's just say the array size is still larger. Let's say it's 29. So 29 does not go into 12. So it's going to give us the calculation 12, 29. It's going to give us 12. So let's just say this is a 29 slot array. I know I didn't draw all the slots, but that's not important. We check in index position 12 to try to put in the word bottle in there. If it's empty, great, let's put the word in there. If it's not empty, then we have to redo this calculation. So we keep doing this iteration. The box that I drew here, we keep repeating these two calculations inside of a while loop. We're gonna keep repeating this until we find an empty slot. Now, the very important thing to keep in mind with double hashing, and I briefly mentioned this to you earlier, and that is that your array size better be a prime number, okay? I'm going to repeat that. For double hashing, it's an absolute requirement that your array size is a prime number. And we're going to ensure this in our Java code when we type it in the next lesson. The array size must be a prime number. If it's not a prime number, your program may crash and burn. Okay, you're going to run into a situation where you may have an infinite loop that just doesn't end, and your program will crash eventually. Let me actually show you an example of that. I know this lecture is getting long, but I don't want to leave anything to your imagination. That information is important for you to understand that this could happen. So let's go over an example of that, where we can have an infinite loop because the array size is not a prime number. I'm going to clear some of this. So if we want to insert bottle, we pass bottle to func1, we get the index position, and then we pass bottle to func2, we get the step size. Once both of these things are calculated, in the code we're going to enter a while loop. And in that while loop, we're going to be continuously trying to find the open slot in which bottle can go. And that while loop, the two calculations are going to continue to repeat. And I just showed you those calculations, but I'm going to rewrite them here in a different flavor so that hopefully it makes better sense. So the index position, which is x, is going to be added to the step size, and it's going to be updating the index. This index, whatever it is, we're going to be doing the mod operator with this index with the array size. The reason why we need to do a modulus with the array size is because this initial index value that is determined by the first calculation is going to be very, very large, okay? Whatever hash value that is determined by the func1, and that hash value could be very large, as you'll see in the Java code. It depends on the function, but if you have a good hashing function, it may return a very large value. And that is why we're going to need mod operator with the array size so that we get the remainder, okay? And that remainder is guaranteed to be one of the index positions within the array, right? If we don't do this, the index might be well out of bounds, okay? It might be much larger than what the array size is. So we don't want to get into index out of bound exception. That is why that's one of the key things in this is we need to do a mod with the array size. And that's going to give us the final index position in this calculation. Okay, and if that index position is not empty, this is going to continue to run until we find an empty slot. Okay, so this is going to be running as part of the while loop. Okay, this is repeating. I'm going to write that right here. This step is going to repeat until we find an empty slot to put the word bottle. Okay, so why is it important? Why is it important for the array size to be a prime number? Let's dive a little deeper and go over an example. Let's say that func1 gave us the index position 0, and when we ran func2, it gave us the step size 5. Now func1 is supposed to give us the hash value, which we're calling as the index. Typically, it's going to give us a much larger number than 0. But to explain to you why the array size needs to be a prime number, I'm just picking this arbitrary 0, so it's easier for you to see the pattern that gets formed when the array size is not a prime number. So let's say that the array size that was chosen is 15. 15 is not a prime number. It's divisible by 3, it's divisible by 5. So we check in the 0th index position first. If it's occupied, then of course we need to enter this while loop. And what does this while loop entail? It entails these calculations. So we have to do 0 plus the step size, 5, and that's going to give us an updated index position of 5. Okay? Then we pass this to 5 mod 15. 15 does not go into 5. The remainder is going to be 5. So now the index position is no longer 0. It's 5. So now let's look at index position 5 and see if it's an empty cell. If it's not empty, we got to remain in this loop and continue with these calculations. Again, why are these calculations happening? These are happening because we are trying to find an open address, an open location in which we can put the word bottle. And we're going to remain in this loop until we find an open slot. So let's just assume that we're not able to find the open slot, and we're just going to continue in this loop, and let's see what happens. So we do that calculation again, and instead of 0, in the second time we do 5 plus 5, and that's going to give us 10. Okay, so the index position is now 10, and we pass in 10 right here. 10 mod 15, that's going to give us 10 because 15 does not go into 10. So now the index position is 10, so we do 10 plus 5 is equal to 15, and then 15 mod 15 is going to give us a 0. Notice that now the updated index position is 0, which was right here. So notice that this is going to happen over and over again. We're back to 0. This is an infinite loop. It'll never end. So the only available slots that we can search within the array, which is of size 15, is 0, 5, and 10, over and over and over and over again. What about the rest of the slots of the array? 1, 2, 3, 4, 6, 7, 8, 9, all the way up to 14. We're never going to get to those slots, okay? The bug is that we've got a non-prime number as the array size, okay? And this is what can happen if you choose a non-prime number as the array size. This is not a prime number. This is divisible by 3, by 5. Now let's say that the array size was 13. I'm going to erase some of this and we're going to redo the calculation. So the positions that will be searched if the array size was 15 would be these, okay? With a 15 array size. But let's say the array size is 13 now in this example. This 13 is a prime number, okay? So you'll see how the result changes. So nothing changes in our calculation. We still have the 0 being returned by func1, let's say. So index position 0 plus the step size is 5, okay? Then we pass 5 into the second calculation, which is 5 mod array size, which is 13. This is going to return us 5 because 13 does not go into 5. 5 is the remainder. So now instead of 0, it's going to be 5 plus 5. That's going to give us 10. And then 10 mod 13 is going to give us 10. So far we're visiting index position 5, 10. You'll see how this changes. So now 10 plus 5, right, the step size, is equal to 15. All right, and 15 mod 13 is going to give us a 2. So in the case of the array size being 13, we're visiting 0 so far, 5, 10, 2. Let's continue the calculation. So now index position is 2 based on our latest calculation. So 2 index position plus step size of 5 is going to give us 7, okay? And 7 mod 13 is going to give us 7. So here's another index position that we can visit in an array with the size 13. So now 7 plus 5 is 12. So 7 plus 5 is 12. And 12% 13, mod 13 is going to give us 12 because 13 does not go into 12. So now we're able to visit 12. So let's keep going forward. 12 plus 5, that's going to give us 17. And 17 mod 13 is going to give us the remainder of 4. So as you can see, because the array size was prime, we were able to visit all of these different positions to find the available slot to put the word bottle in. Since the array size is a prime number now, we're going to be able to calculate all of the different index positions, and those are going to be from 0 all the way to 12. That's how you get the 13 slots. From 0 to 12, we'll be able to visit each one of those index positions in our search for finding an open address. In the case that the array size was not a prime number, in the first example, these are the only slot positions we could have visited, okay? And this algorithm would crash and burn. So it's very important for your array size to be a prime number. Now, a subtle but important point that I like to make about func2, which is a step size function, is that it must not be the same as the func1, right? The logic to retrieve a new hash that's used in func1 better be different than the logic that's used in func2. That's an obvious, right? Otherwise, it would defeat the purpose of having function 2. Another point is that func2 must never output a 0, okay? Which means that there's no step size, right? If it returns a 0, there would be no step. Every probe would land on the same cell, and the algorithm would go into an endless loop. So just keep these 2 points in mind. This is an important lecture. If you miss something, if you don't understand it, I recommend to rewatch it, or if you kind of get it, that's okay. You can move to the Java code, type that out, and then you can always come back to this and get a refresh on the theory, and everything will make a lot more sense, okay? So let me wrap it up here. Thanks for watching. I'll see you in the next video where we code up the double hashing hash table.